Alright, I'm playing around with some of the regulators that I got for the project. I've got two of them here. There's a microchip one called a 1703 and then another microchip one that's called a 1824. And this one has got a additional feature besides just being a 3.3 volt low dropout regulator. It's got a undervoltage lockout protection feature, so that at 1.8 volts it will turn the regulated output off. And I wanted to test it out just to see if maybe I could use that as a battery protection feature for my lithium polymer batteries that I'm planning on using in the mom's timer. So one of my multimeters is about to go off. So I've got my two multimeters here hooked up, and I might have to flip the power on and off to the circuit again to make it work. But so the bottom multimeter here is showing the output voltage from the voltage regulator here, this lower one, which is that 1824 one, which has that under voltage lockout feature. And then the top one is showing the current draw from this battery pack and voltage regulator that I got here, where I've got 3.9 volts going into this thing, and then it's outputting 3.28 volts. So if I change this to microamps, so it's drawing 114 microamps, just doing its regulated output of 3.3 volts. And in the data sheet, that's exactly what it says will happen. The input quiescent current is typically 120 microamps, and it can go all the way up to 220. And so it's drawing 114 microamps according to this, so that's pretty close. And I didn't know that quiescent current meant this, so I'm just learning here. And 120 microamps is that busts the idea of using this regulator anyways for powering especially the key fob part of the timer that's going to have this little 80 milliamp battery in it, or something similar to this. So you know, I want to get that down a lot lower than I want it to be like 10 microamps or less. So this is going to be too much, but at least I can play around with this thing and see if that undervoltage lockout part works. So it's supposed to kick in at like 1.8 volts, so I'm going to try that out. Okay, I turned my little power supply here down to 2.2 volts, and it's still able to output, I guess 1.8, 1.9 volts, and it's drawing 206 microamps, and that does fit within this maximum specification still. So it's drawing more microamps since this voltage is lower. Okay, I'm going to go below 1.8 now and see if this shuts off. It's supposed to, it says input quiescent current when it's shut down is supposed to be 0.1 microamps, max of 3. So we'll see if that happens. Okay, I turned it down, and it did turn the output voltage totally off, but it is showing a current draw of 14 microamps, not 0.1 microamps or 0.1 to 3 microamps. But this does say the shutdown, not when the undervoltage regulator kicks in. So there's a pin that's called shutdown. I think it's this orange one here. Let me see if I could do this. If I move this pin to the shutdown position, which is supposed to be ground. Okay, yeah, that did it. That totally, my meter can't read it anymore. So the shutdown, okay, so this shutdown, the pin that's called shutdown, it is working as expected. Let's see, does this show the shutdown? Yeah, so here it shows the pin. There's a shutdown pin on this SOT23 package, pin number 3. So it does actually kill it if you draw that pin low. but it doesn't kill the output all the way just based upon the voltage. So the undervolt regulator or undervoltage feature that it's got, that doesn't really work for me either. This is that undervoltage lockout. So that when that locks it out, it still draws 14 microamps. So okay, well, it's interesting to know. I got like 5 of these, so I'll know in the future for something. But yeah, these aren't gonna work. They draw too much power. Okay, I've got the 1703 voltage regulator hooked up here, and I've got my power supply outputting 3.31 volts into it. So I changed this up so this shows the input voltage into the regulator, and then this is the current draw from that the regulator is consuming. So it's consuming 5 microamps. If I come here and I turn the input voltage down a little bit, look at that, bam, it went all the way up to 92 microamps when I turned it below the voltage regulator input below 3.3. I tried to put larger capacitors on the input and output. I currently have 1 microfarads ceramic ones here, so I put these 4.7 electrolytic ones on here to see if that would help it, because I don't think it's supposed to do that, but like the data sheet doesn't say anything about it. It just says that it has a minimum input voltage of 2.7, but I might have to read through the whole thing because this is very, very strange. So anyways, as long as it has enough voltage, it does okay, but when it gets below 3.3 volts, the current draw goes way up above what I would want it to be able to do for the mom's timer project. Okay, now I'm taking a look at the power draw of the microcontroller. I've basically got this microcontroller set up to act like a Arduino Pro Mini now. I've got an 8 megahertz crystal on there, and I've got a little program on here where if I click this button, it will wake up the microcontroller. It'll turn on this LED for 10 seconds, and it draws about 10 milliamps when it's awake, and then it goes back to sleep after 10 seconds. And when it's asleep, it doesn't draw hardly anything. So on the microamp scale, sometimes this will go up to 0.1 microamp, but it kind of bounces between 0 and 0.1 microamp. So it really is very much asleep, and that's exactly what the data sheet says it should be able to do as well. So in the data sheet for the microcontroller, with the watchdog timer disabled, you should be able to get from 0.1 to 2 microamps. And so this one is agreeing with that right now. And I've got that 8 megahertz crystal in there, and it should be, when it's awake, it should consume between 4 and 9 milliamps. So if I change this to milliamps, and then I hit the button to wake it up for 10 seconds, it's drawing 9. If I get rid of the LED here, it's drawing, it went back to sleep, so I'll just hit the button to wake it up again. So it's drawing about 4 milliamps, 4.1. So that's right in line with this. Okay, so I'm going to try this at 16 megahertz just to see what the power draw is like. I just went over to my environment here, and I changed my board to be the Arduino Uno because I know that one runs at 16 megahertz. And then I've got my my good old AVR Dragon here plugged in, and I just hit the burn bootloader to upload the Arduino Uno bootloader onto this microcontroller. And it says it's all done, and now what I'm going to do is I have to switch out the crystal, that 8 megahertz crystal right there. I need to put a 16 megahertz crystal in there, and then I'll be able to program that. Okay, it programmed just fine. Basically, I got an Arduino Uno now, and when it's asleep, it's still showing between 0.1 and 0 microamps, so no difference there. And then if I click the button to cause it to wake up. It does draw more power. I might have to hit that button again because it might have not had power to it. But yeah, so you can see it's drawing, it was doing 4 milliamps before when it was running at 8 megahertz. But now it's drawing between 6.5 to like 7.5 milliamps when it's running at 16 megahertz. I might be able to get by with running this at 1 megahertz. I'm not sure. I'll see. Maybe I'll see that. I'll test it out next. Okay, I was able to get 1 megahertz test all set up here, and I've got this on microamps, and it's drawing between 0 and 0.1 microamps on, according to this meter here right now. It's asleep, and I'll hit the button to wake it up, and it goes up to about 1.8 microamps when it's or 1.8 milliamps when it wakes up. And so that's compared to the 4 milliamps when it was running at 8 megahertz. So this time it went up to about 1.5 milliamps, and it falls right back to sleep. So yeah, that's kind of neat that you can make this change via software actually on the fly, and you can save a lot of power. So maybe I can take advantage of this. The way that I did this, had to look online, and the data sheet for the microcontroller, there's this system clock prescaler that you can modify. What it does is it defines how fast it's going to run everything based upon your system clock, and you can divide the system clock by 1, or in my case I wanted to divide by 8 because I've got a 8 megahertz crystal in there. Divide it by 8 so it'll run at 1 megahertz. And to make a change to the system clock with this prescaler, it's a 2-step operation. You've got to write a 1 to this change enable bit that's in the register, and all the other bits need to be set to 0. And then within 4 clock cycles, you need to write the bits that define what kind of division factor you want for the prescaler, while setting the CE back to a 0. And so the register that all this is in is right here, clock prescale register, CLKPR, and then the 7th bit, or I don't know, the 8th bit is the change enable bit, and then here's where you can select which division factor you want. And there's a table down here that shows all the available clock division factors. So to get an 8, you need to write a 1 to PS0 and another 1 to PS1. That'll give you an 8. So within my little test app for testing out power draws here, what I did right in the setup here was I did the 2-step process. First I wrote a 1 to the change enable bit in this register, and I just set the register equal to that, and that basically just made this one a 1 and all the rest of them a 0. And then I set PS1 and PS0 to be 1, and all the rest of the bits are equal to 0, and so that does it, and it worked just fine. The downside to doing this is that functions like delay, they don't know that you've changed the clock speed on it, and so when you put a delay of 1,000, it's actually going to delay by 8,000. So there's probably going to be a lot of other functions that are in the Arduino libraries that are messed up with this. So it's neat that it's available, and maybe I'll be able to take advantage of it, but it might be a little tricky to get everything to work just right. My last test of power consumption that I wanted to do today is all set up and working now. I wanted to see what kind of power draw the ATtiny would have when it's asleep and when it's awake. I've got it running at 8 megahertz because that's the minimum speed you can use with software serial, which I'm going to be using to help me debug it and create the software for it. And I'll try running it at 1 megahertz. I'm sure it'll do just like the ATmega did when it was running at 1 megahertz using less power. But for now I've got it at 8 megahertz and it's asleep, and it uses 0.1 to 0.2 microamps. And then when I click the button to cause it to wake up, it uses 3.6 milliamps. So very comparable to that ATmega microcontroller. And then in a little bit, so it goes right back to sleep. So to get the sleep working and getting the button to work, let me just show the button setup I always use is I just have one side of the button pulled down to ground, and then the other side is hooked up to the pin on the microcontroller. And then I just I use the microcontroller's pull-up resistor on the pin to pull it up to high. And so when you push the button down, it just causes it to go low because it's grounded. The attach interrupt call, this was a little bit of a trick. I had to use the word low instead of the word falling that I've been using all the time with ATmega microcontrollers. It took me a while to figure that out. It was somebody put it on the forum, a forum somewhere, and I tried it out and that finally worked. So you got to use the word low for the ATtinies at least. The sleep, I had to modify my sleep routine. This is the one I use for the ATmega, and specifically disabling the brownout detection logic. I just had to move that up. This stuff here, getting the order of it right is important. You have to complete certain operations with a certain number of clock cycles for them to be accepted by the microcontroller. And for some reason, when I had it down between the sleep enable and the interrupts, it wasn't working on the ATtiny. I just moved it up above that there, and it worked just fine. The ATtiny didn't have any definitions for these particular bits in this particular register though, so I had to put a couple defines in to define the BODS bit is in position 7, and the brownout SE bit was number 2. So yeah, I just had to reorder those things, and then it would finally start to sleep. And yeah, that was it. So good day, and I got to see what the power consumption is going to be like on just these raw microcontrollers, and got to see that I'm going to have to use one of these battery protection ICs for protecting the lipoly batteries from over discharge, because that one voltage regulator that I was going to try out, it's just not going to work.